Yeah, thank you, and I want to thank the organizers for inviting me to speak. It's a real honor for me to be speaking as part of this occasion, and it's also been absolutely wonderful this week to get to learn more about the mathematics that Professor Umo has worked on, and yeah, it's this very diverse and beautiful range of topics that have been covered. So I'm going to start with some very general background. Maybe I'll start in the center. About the Bloch-Kato conjecture, but sort of beginning with the Birch and Swinnerton-Dyer conjecture for elliptic curves, which is maybe more familiar. So let me just start in the context of an elliptic curve over the rational numbers. Let's say we're just defined by a Weierstrass equation such as this. And so the conjecture of Birch and Swinnerton-Dyer, which dates back to the 1960s, asserts the equality of two numbers that you can attach to this elliptic curve. So one of them is the Mordell-Weil rank, which you get by looking at all the solutions, the Q points of this elliptic curve, so solutions of this equation over Q. Those form a finitely generated abelian group, and you take the rank of that group. And on the other hand, you have the order of vanishing at s equals 1 of an L function associated to S, which is given by an Euler product. To remind you, it looks a little like this. So I'm leaving out some factors at primes of bad reduction, but sort of most of the Euler factors look like this, where AP here you get by counting the number of solutions to the elliptic curve now modulo P. So for every prime, you look at the solutions mod P, you put these numbers together into some complex analytic function of S, and the sort of very remarkable conjecture is that the order of vanishing of this analytic function is detecting the rank of the group of rational points.
So even the fact that it extends to S equals 1 is non-trivial.
Yes, that's right. Yeah. So when this was formulated, it was not even known that this made sense. So yeah, it's only because we now know that elliptic curves over Q are modular that it's known this is even a sensible thing to write down. So yeah, when it was formulated, it was an even more sort of startling conjecture than today for that reason. And for some context, what's known towards this, it's basically known when the order of vanishing of this L function is at most 1. So this was due to the work of Colli-Vaughan and Gross-Zagier, combined with Carl Rubin for the CM case. This was all in the early 90s. So that's sort of the state of the art. But the question that motivates the Bloch-Kato conjecture is sort of in light of this BSD, the question is, what is the arithmetic meaning of orders of vanishing of other L functions? So, there aren't L functions exist in in a lot of different settings besides that of elliptic curves. In the elliptic curve case, you have this really amazing interpretation in terms of arithmetic. So it's natural to ask if that exists in other settings. So there's a conjectural answer to this proposed by Bloch and Kato. Also in 1990. Who worked in the setting of geometric p-adic Galois representations. So geometric here can have two meanings. So for the purposes of this talk, it's going to mean that it's a subquotient of an etale cohomology group for some x over q that's smooth projective. So this is a representation of the absolute Galois group of q. So that's one possible meaning. You can also put some conditions, some more intrinsic conditions on the Galois representation v that are expected to imply this. But for the purposes of this talk, this is fine. And to such a thing, on the one hand, you can associate an L function. So you can get this again as an Euler product. And again, I'm going to be a little sloppy about finitely many places. But for good primes and L not equal to P, the Euler factors look like this. So you take the characteristic polynomial of Frobenius acting on the Galois representation, and you want to plug in L to the minus s, where s is a complex parameter. Okay, now, of course, a priori, this is a QP vector space. The characteristic polynomial has QP coefficients. But in reality, because of the Weil conjectures, the coefficients will actually be algebraic. So this is a reasonable thing to do. So this L function, by the way, you can also see as part of the Hesse-Weil L function for x, if you like. And the conjecture is that the order of vanishing of this L function. So let me actually write it sort of larger. Wow, that went really high up. Okay. Okay, the conjecture is that the order of vanishing. So again, this L function is not actually known to be defined at s equals 1 in general. It's expected to be. And this is supposed to be equal to the dimension of something called the Bloch-Kato-Selmer group of V. So I'll tell you what that means. Oh, and there's a correction term for the dimension of Galois invariance. That's not so important. That's only there because if you have the trivial representation, the L function will be the Riemann zeta function, and so it'll have a pole. So this is correcting for the poles that you would get from the trivial part. That won't be very important for this talk. So you're supposed to take the dual, but I kind of cheated in my definition of the L function so that you don't have to. The Galois representations I'll use will be self-dual, so it won't matter. Yeah. Okay. So this Bloch-Kato-Selmer group, I won't write down a full definition, but I want to give you the shape of the definition. So it's a subspace of the Galois cohomology. So this is continuous group cohomology for V as a representation of the Galois group. It's a subspace that's defined by local conditions. So you're looking at classes so that for every L, when you restrict to the decomposition group, which is a subgroup of the absolute Galois group, then those local classes lie in a prescribed sort of local subspace of Galois cohomology. So away from P, these are actually just unramified classes. At P, you should do some p-adic Hodge theory. But the precise definition doesn't matter. What's important is that they're Galois cohomology classes, and that this Selmer group is a highly arithmetic object. So you should think of it as a kind of replacement of the Moore-Delvey group that makes sense for any p-adic Galois representation. And in particular, let me give the example that relates it to actual BSD. So when E is an elliptic curve.
So you have to assume that it's a de Rham representation locally, or?
Well, that'll be true if it comes from geometry. But if you want to, that would be go into the definition of sort of the intrinsic version of the definition of geometric. Yeah. So if you look at an elliptic curve, the sort of associative V would be the p-adic Tate module, which you can also get as first etale cohomology twisted by 1. So it's of this kind. So if you look at the L function for this Galois representation, it's exactly the usual L function of E. So that's the same. And so then if you kind of compare this conjecture to BSD, on the one hand, you have the Mordell-Weil rank, and on the other hand, you have the dimension of this Selmer group, which is actually the usual Selmer group, if you're familiar with the one that shows up in the theory of elliptic curves. And the relation between them in general is that the Selmer rank is an upper bound for the Mordell-Weil rank, and it's expected to be equal. So sort of up to this, so this is the Tate-Shafarevich conjecture. So up to this conjectured equality, you can see that this really does kind of recover and generalize BSD. But again, the Selmer group is somehow a more flexible object that makes sense in more contexts. OK, so that's sort of the basic background for the talk. So let me now introduce the actual setting we're going to be working in. So the Galois representations we're going to study are related to automorphic representations. So we're going to fix, and I'll remind you what all the words in this sentence mean. We're going to fix an automorphic representation of GSP4 with trivial central character, and where pi infinity is discrete series of weight 3, 3. Okay, so to backtrack a bit, first let me recall the notion of an automorphic representation. So the space of automorphic forms for GSP4, or you can run the same definition for any group. This is a certain space of nice functions, where I'm going to be a little sloppy and not write down what I actually what conditions you actually need, but some kind of functions on the adelic points of the group that are left invariant by the rational points, where those are kind of embedded diagonally into the adeles. So you can see that on this space of functions, there's going to be an action of the adeles of GSP4 by right translation, which is preserving the left invariance. And an automorphic representation, which I'm going to write as AR to abbreviate, is an irreducible constituent of this space of automorphic forms as a representation for GSP4 of the adeles. So in particular, one thing you can always do, because it's irreducible, you'll be able to write it as a restricted tensor product, where pi v is a representation of the local points, GSP4 QV, for every place of Q.
I'm sorry, I'm
yes.
Going back, but with respect to the question on LBS, FR is the Frobenius, the
yes.
arithmetic or the
arithmetic Frobenius.
Arithmetic, yes. So that's where you are cheating. But also, for the value at s equal to 1, is there a restriction on the weight of the motif?
I don't think so. I think it should hold. It should hold no matter what. Yeah.
What is why the letter AR?
That's my abbreviation for automorphic representation.
And in the conjecture, V is what? Any?
You're asking about V's?
V is a geometric.
It's a geometric p-adic Galois representation, so it appears in etale cohomology.
And there was a question about the dual that you said that actually.
Yeah. So usually the convention to define the L function is different. So I've messed with the convention by putting for arithmetic instead of geometric Frobenius in the characteristic. Okay. So those are the objects that I'll be talking about. So the conditions I put here, trivial central character, that just means, of course, because this is irreducible, the center of the group is going to act by a character. I want that to be trivial. And the condition on the weight, I'll say a little bit more about, but it's just this Archimedean component of pi has to be some particular thing. It's analogous to asking for weight 2 for classical modular forms. Okay, and to such an object, you can associate, and this is part of the global Langlands program, but it's known unconditionally. You can associate a compatible family of p-adic Galois representations. So here E is some sufficiently large number field. It'll contain all the Hecke eigenvalues of pi. You don't have to, yeah, if you'd prefer, you can imagine it's always Q. And for every place of E, we're getting a Galois representation valued in GSP4 of that completion. And you can characterize these by some, for instance, looking at the characteristic polynomials of Frobenius. And there's also a normalization that you have to pin down. So here I'm normalizing these such that they're self-dual, meaning if you take linear dual and Tate twist by 1, you get back rho pi p. And I'll put one more automorphic assumption, which is that pi is not cap or endoscopic. So these are some automorphic adjectives, which I won't define because they're not really necessary. For the purposes of this talk, what they mean is just that rho pi p is going to be absolutely irreducible as a 4-dimensional Galois representation. OK, so that's the setting, and let me tell you the first main result of this talk. Yes, it's known if P has residue characteristic at least 3, or maybe at least 5. I'm not sure. Either way, that will implicitly be in the assumptions of the theorem. Yeah, but it is expected. Yeah. So with pi as above, I have one more technical condition. I want to suppose that there exists a prime L such that pi L, so this local representation, is something called type 2a, which I'll explain after I've stated the theorem. But it's some kind of mild local ramification that you can have. OK, then the conclusion is that for all but finitely many primes p, you get the rank 0 case of Bloch-Kato, in that if the L value is non-zero for rho pi p, then the Selmer group vanishes. So here, and here this L value, although I've written it depending on p, it's actually just the global spin automorphic L value of pi. So really there's just one L value that's controlling the Selmer groups for all but finitely many primes. And just sanity check, the consistency of Bloch-Kato is that if this is non-zero, then the order of vanishing is 0. So you expect the dimension of the Selmer group to be 0, and that's what you get. OK, so a few sort of remarks on the statement. So first, the type 2a assumption. You can describe it in terms of representation theory, but it's easier to just think about it in terms of the associated Galois representation. It means, as long as L is not equal to P, it means that the Galois representation is going to look like this. So you've got the cyclotomic character. So when you restrict your decomposition group at L, you've got cyclotomic, trivial, something unramified. And here you have a non-trivial ramified extension. So it's ramified, but in some kind of very simple way. This is playing a few roles in the proof, which I'll try to point out as I go. But it's a technical condition that's not expected to be necessary. The next assumption, or the next remark, is that this all but finitely many primes is really very explicit. So I just didn't want to write down all the conditions on the board. But it needs P to be a prime of good reduction. So pi P should be unramified. And the image of the mod P Galois representation. So you take some Galois stable lattice in rho pi P, you reduce mod P, and you get some mod P object. This is sort of large in some sense. It's not going to contain, it doesn't have to contain all of SP4 FP or something like this. But there are just it needs to be absolutely irreducible, and there are some elements you need in the image. So one of the roles of type 2a is actually to make sure the image is large enough. So yeah, having these elements already kind of tells you some things are in the Galois image. And the final remark I want to compare this theorem to the work of Loeffler and Zerbes from 2021. So they proved a similar result with actually more general weights. So this condition I put on the Archimedean part, they can relax, but they can only get primes p that are ordinary. So that's some kind of, so that might sound like not such a bad condition to be ordinary. And it's expected to be true for 100% of p, but it's not known for a general pi like this if it's true for any p at all. So it is kind of nice to avoid ordinarity if possible. And the sort of difference between their approach and mine is that I'm really not using any p-adic variation. So p-adic variation is sort of very powerful for moving around the weight and doing things like this, but it relies on ordinarity in this situation. Okay, so that's the statement of the theorem.
Yes. A small question. P as above, it means geometric in your sense, but geometric, does that mean that it's a subquotient defined over QP, or it might be defined over some extension of QP?
So it's actually, I mean, I think you could also, it depends on how you want to realize it, but yeah, you can. So when I said, first of all, I said pi is above, so that means pi is an automorphic representation like this. But so rho pi p, I guess you want to extend scalars first, and then you'll see it. Yeah, but this, okay, so before I sort of, so this was something about rank 0 Bloch Kato. I'm also going to say something about rank 1 Bloch Kato. But before I get there, I first want to tell you more about how rho pi p is constructed, because that'll be kind of relevant to the statement in rank 1. So this is a story that's due to mostly to Taylor, and then sort of some loose ends were tied up by Lemon and Weissauer. So this is how this compatible family of p-adic Galois representations was constructed. So we're going to find them in etale cohomology of the Shimura variety for the group GSP4. For the purpose of this talk, it's best to think of this as a moduli space of principally polarized abelian varieties of dimension 2 plus a level structure. I won't be super specific about the level structure, but it depends on this choice of compact open inside GSP4 of the finite etales. Okay. And this object is usually called the Siegel threefold. So it's a very classical and nice Shimura variety. And if you look at the etale cohomology of this guy, so the most interesting part of the cohomology lives in degree 3. So I'll use this EP for convenience so that it breaks up properly. So then this, also I want to take here the interior cohomology, so the image of compactly supported cohomology inside regular. The role of this is that it will throw away some boundary contributions to the cohomology, which aren't as relevant for this. And so this cohomology, it comes with two commuting actions. So first, it's got the Galois action that you always get on etale cohomology. This is always base change to Q bar. And it also comes with a Hecke action that depends on the level K. And this is some large algebra of correspondences that's keeping track of isogenies between different principally polarized abelian varieties. So you can decompose with respect to this action, and it has this very nice form. So the Hecke actions are all given by the action on finite parts. So here pi f is the finite part of an automorphic representation of GSP4, where pi infinity happens to be discrete series of weight 3, 3. So this is the reason for that condition before. These are exactly the rho pi p's that appear in this cohomology. And the Galois representation you get attached to here is rho pi p, at least if you put the correct Tate twist on your coefficients. Okay, so this is how it's constructed, and you can see from this that rho pi p actually is geometric in the sense asserted before. You might be worried that this isn't compact, but because we're looking at interior cohomology, you could just take any sort of nice compactification you want, and this Galois representation is going to persist there. Okay, and so now I want to sort of, now that we know where rho pi p comes from, let me back up a little bit and tell you about an expected connection between Selmer groups and geometry. So this is sort of a general story. So this works for any smooth projective algebraic variety X. So choose any R up to the dimension. And we're going to look at the Chow group of codimension R algebraic cycles, but the cohomologically trivial part. So this is cohomologically trivial codimension R algebraic cycles on X. And also assuming that P is a prime of good reduction, for simplicity, there's a construction called the Abel-Jacobi map, which takes as input one of these cohomologically trivial algebraic cycles, and it outputs an element of the Selmer group. For the Galois representation, that's the 2R minus 1 etale cohomology of X with a Tate twist by R. So yeah, I won't explain the construction of this, but it's coming from some kind of spectral sequence. So usually the cycle class of a codimension R cycle would live in H2R. And so here that one vanishes, but you get something where sort of one of the cohomological degrees has shifted to Galois cohomology. And so that would just tell you it's a Galois cohomology class, and then using that P as good reduction, you can show it actually lies in the Selmer group. And it's expected. So this is part of sort of a larger story called the Bailenson-Bloch Kato conjectures. But one sort of piece of that story is that the Abel-Jacobi map is an isomorphism, at least after you tensor with QP. I mean, it shouldn't be before because you expect this to be finally generated. But so this is sort of a very deep conjecture, but it tells you the Selmer group is supposed to be capturing something about geometry. It's supposed to be capturing cohomologically trivial algebraic cycles. And this gives you a clue if you want to say something about Bloch-Kato for rank 1 in this situation, that you should look for some algebraic cycles as the source of your Selmer classes. Actually, sorry, I just meant to mention back here, for context, there's the elliptic curve case. So here, this is the usual Kummer map. So the cohomologically trivial codimension 1 cycles are just the rational points of E, and the Abel-Jacobi map lands you in the Selmer group. And so this sort of expectation over there is the same conjecture we saw before, that the dimension of the Selmer group is the same as the rank of the Mordell group. This map is actually known to be injective modulo torsion for the elliptic curve case, although it's not known in general. Okay, so to get back to sort of the story at hand, so we're interested in the variety, the Siegel threefold. And if you think about the numerology, if we want to get Selmer classes for rho pi p, which appeared in middle degree 3, you want R to be 2. So you want to look for some codimension 2 algebraic cycles, which would be curves on this threefold. And there's a very natural source of such things that comes from taking B, an indefinite quaternion algebra, over the rationals, and considering this Shimura curve, which I'll write as x sub b, which is a moduli space of principally polarized abelian varieties of dimension 2, plus the action of a maximal order inside B, plus some level structure, which I'm not going to be very precise about. But you can kind of see immediately that there will be a natural map from xb to the Siegel threefold, at least if the levels are chosen compatibly, by just forgetting the action of this OB and only remembering the underlying abelian variety. In fact, this will be injected if you choose the levels nicely. I'm also, let me just say this won't play much of a role, but just for precision, I also want to allow any Hecke shifts of this kind of embedding. So messing around with the level structure sort of any way you want. Okay, so if you look at the cycle class of this guy, this will live in Chow 2 of our Siegel threefold. Now, it doesn't have to be cohomologically trivial in general. However, what you can do is you can kind of localize at the Hecke eigensystem of pi, and then it will be forced to become cohomologically trivial because this Hecke eigensystem won't appear in degree 4. So there's sort of nowhere for it to go in H4, so it has to go to 0. And then you can make sense of the Abel-Jacobi images, which will lie in H1F, so the Bloch-Kato-Selmer group of...
The first one probably in the modular, the kernel of Abel-Jacobi, because I mean to really want to get a pi f eigencomponent, because the Galois group acts on CH2 is not necessary. I mean the Hecke operator CH2 is not a modular. We don't know.
Yeah. So you could just localize at the maximal ideal of the Hecke algebra. I mean, it doesn't really matter how you do it. Somehow or other, you should project at some step. You should project into the right eigenspace. But yeah, in general, this Chow group doesn't break up.
And you have a purity argument to know that it's okay.
Yes. Okay. Exactly. To know that that we can put this f here. So it lands, and you can extend scalars here. That's okay too, and it'll land, or you can kind of project into the pi f part, and then this is just going to be pi fk. So just this finite dimensional Hecke module, tensored with the Galois action, the Selmer group of the Galois part, which is rho pi p, because the Galois action here is trivial. Okay, so this is some construction of kind of canonical elements in the Selmer group.
What is E2 here?
So this is just some this is your sufficiently large number field. This is a place. Yeah, this is your coefficient field, and this Tate twist by 2. Yeah. Okay, so then the second main theorem of the talk is, so with pi as above, so really all the same assumptions as theorem A. Then for all but finitely many p, if there exists some b such that this Abel-Jacobi image is non-zero, then the dimension of the Bloch-Kato-Selmer group will be exactly 1. So of course you know it's going to be at least 1, because if this is non-zero, then you've constructed a non-zero element. So the content of the theorem is that if one of these classes is non-zero, there's no space left for any other classes to exist in the Selmer group.
Do we know that all these classes are collinear in the Shimura group?
Not a priori. Yeah, so there's, I guess there's a modularity statement which should maybe imply they are, but it's not obvious immediately. Whoa. Okay. Yeah, in fact, I think it's not. Yeah, I think it's not clear even from the modularity. I think you need this theorem to know it's true. Yeah, but so I want to explain. So this theorem, as it's stated, you don't see any L functions. So maybe that's a bit disappointing. Because Bloch-Kato is supposed to be about L, orders of vanishing L functions. So let me explain kind of the conjectural connection to L functions with these cycles. So, sorry. So this has kind of two pieces to it. So the first expectation is that there should be some kind of Gros-Zagier type formula that relates the derivative of the spin L function of pi to some kind of height pairing that involves these xb's. I'm being a little imprecise because it's a bit complicated to state. So you really want to take a generating series of these things and sort of pair it with a certain modular form and then use that to take the height. But nonetheless, I mean, what you can at least conclude is that what you expect to be able to conclude, so this is called the arithmetic inner product formula, and it's not known, but it is conjectured. And a unitary analog of it is known. So if you had this formula, then if the derivative of this L function were non-zero, then this would immediately tell you that these are non-trivial in the Chow group. And the second expectation, which is part of the valence and Bloch-Kato conjecture I mentioned before, is that the Abel-Jacobi map is injective. So as soon as you have non-zero classes in the Chow group, you should actually get non-zero Selmer classes. So if you put those together, then you would get, if the derivative is non-zero, then the Selmer group is rank 1. And let me also put this into context for you with the history of BSD. So BSD in rank 1 was kind of proven through 2 steps. So first, Gros-Zagier showed that the first derivative being non-zero, not equal to 0, was equivalent to the existence of a non-torsion Heegner point, which is some kind of special point in the Mordell group. And then Kolyvagin kind of independently proved that if, for the same sort of special Heegner point, if its Abel-Jacobi image is non-zero, then it generates all of H1F. It generates the whole Selmer group. So you can see that kind of the Gros-Zagier part is this kind of expectation. And what this theorem is doing is essentially the Kolyvagin part of that theorem. Okay, so in the time that remains, I want to explain to you kind of ideas of the proof. I will only really have time to talk about the proof of theorem A, but the proof of theorem B kind of uses the proof of theorem A. So if you want to hear about it later, feel free to ask me. So, I mean, both of these theorems are really about bounding Selmer groups. So Theorem A, you want to show the Selmer group vanishes. Theorem B, you want to show it's kind of no bigger than the class that you already have. And so there's really only kind of one game in town for bounding Selmer groups, and that is producing ramified Galois cohomology classes. So let me sort of write down what that means in my context. So we're going to produce some classes indexed by auxiliary primes that I'll call Q. So these are just, like, primes not dividing the level that you'll choose in some appropriate way. And they'll be valued in the Galois cohomology, not of rho pi p, but actually of its reduction modulo p. So they'll be torsion. And they have to satisfy two properties in order to be useful for bounding the Selmer group. So the first property is that C of Q should be unramified outside Q. And at P, that means something p-adic-Hodge theoretic. And the second condition is that, at least under this assumption that the spin L value isn't 0, you should be able to show that the restriction of C of Q to the Galois group, or in particular even to the inertia group at Q, is non-zero. So they should be unramified outside Q, but at Q they should be ramified. So they should fail to be Selmer here. Now the reason this is what you want is a little involved to explain, but just the shape of it is that there's some Poitou-Tate duality argument where if you can kind of systematically produce classes like this, you take your purported element of the Selmer group and you'll pair it against classes like this and you'll get a contradiction. So a few things I want to point out about the structure of this. One is that property 2 is obviously sort of the key thing, because if you don't require this ramification, you could just take the 0 class, and obviously that wouldn't do anything for you. The other is that I'm writing everything mod p for simplicity, but really to get the full strength of the theorem, it's much better to work mod p to the n. That's actually what happens in practice. Okay, so that's kind of the basic idea, but let me tell you where these C of Qs are supposed to come from. So they're constructed from geometry. And the method follows an idea originally due to Bertolini and Darman in the modular curve case. But let me explain how it works here. So we're going to take L to be that place from the very beginning of the theorem statement where pi L is type 2a. So it's some prime. Actually, what's needed here is that it has pi L as a local Jacobi-Langlands transfer, and hopefully I'll have time to say why that's needed. And then I'm going to consider the quadratic space VQL. So this is a quadratic space over Q, like equipped with a quadratic form, which has signature 3, 2, and which is ramified at Q and L. So what's happening here is that there's a local global principle for classifying quadratic forms, and you can see that if you want to have signature 3, 2, you need to be ramified at an even number of finite places. So if you want to, so our sort of objective is to introduce the ramification at Q, but you have to also introduce the ramification at L. Okay, and then we're going to consider a Shimura variety for the G spin group of this quadratic form. Now, if you want to think about it as the SO group, that's fine. It doesn't really matter. G spin is better for technical reasons. But what you should know is that this is an inner form of GSP4. So this is using the exceptional isomorphism that PGSP4 is SO32. Okay, so this is some kind of Shimura variety. It's kind of like a twisted Siegel threefold. So it has the relation that the quaternionic Shimura curves have to classical modular curves. And you've kind of introduced some ramification into the situation at the prime Q. In particular, this has bad reduction at Q. And so that implies that it's possible for this, for its etale cohomology, can be ramified, and in fact it is ramified at Q. And you can show using, so that's possible because it has bad reduction, but you can actually show using automorphic methods that it's so ramified at Q that rho pi p cannot appear. So Q is an auxiliary prime, so rho pi p is unramified at Q. And they're essentially because of how Jack A. Langland's transfers work between GSP4 and this group, rho pi p being unramified at Q cannot be in this. So you cannot use this Shimura variety to construct Selmer classes for rho pi p. However, what you can do is use the following proposition. So there's a proposition that if Q is level raising, and this is in quotes because I'm not being super precise about the exact conditions I need, but I'll sort of try to say it in words. If Q is level raising, then there exists a map, in fact a surjection, from the cohomology of this sort of new ramified Shimura variety, and now with integral coefficients. This will surject onto rho pi p bar. So here O is the ring of integers in our coefficient field EP. Okay, so this is sort of an interesting result because rho pi p doesn't appear. So the fact that it's appearing mod p is witnessing a congruence between pi and some things that are actually appearing in this cohomology. So that's why it's called level raising. It's a manifestation of some kind of level raising congruences of automorphic forms. Now level raising here means that the Frobenius eigenvalues of Q satisfy some kind of condition, some kind of congruence condition that makes it possible for this to happen. And the proposition is that it does actually happen. So in particular, you can use this to make Galois cohomology classes valued in rho pi p bar. So let me sort of explain how that works. So you still have special cycles, which are still going to be these same old quaternionic Shimura curves. You can think about these in the moduli interpretation. This is still a PEL type Shimura variety, but you can also just think of this group theoretically as this is like G spin 2, 1 inside G spin 2, 3 is kind of the underlying group theory. And so in particular, we can still make some Abel-Jacobi images. Now, in order to make the class cohomologically trivial, so now we want to localize kind of integrally at the correct Hecke eigensystem. And we're using a non-trivial theorem here. It's actually very related to what Mingzhe was talking about on Monday, to show that this will be cohomologically trivial after you localize integrally at the maximal ideal corresponding to the correct Hecke coefficients, or Hecke eigensystem. In any case, it is cohomologically trivial, so you can take Abel-Jacobi, and you end up with a class in here. And we can use the proposition to then map this into H1Q rho pi p bar. So the image of this class I'm going to write as CQXB. So we want to use these CFQs in the proof sketch. And so actually we've constructed sort of more than one because we get something like this for every B. But sort of all you need is that if the spin L value is non-zero, then you want there to exist some B such that CQXB is ramified at Q. So as long as you have one of them, you can just take that to be the prime in the sort of Galois cohomology argument that, that allows you to bound the Selmer group. Okay, so I'm going to now, sort of in the last maybe 10 minutes or so that are left, I'm going to try to explain to you sort of how you relate this ramification to the L value, which is really kind of the key point. So let me first give you like a very schematic outline of how this works. So here's the schematic picture. So you start over here with information about the spin L value, which is analytic information. And you want to get over here to the ramification of CQXB, which is sort of much more algebraic information. And they're going to end up meeting in the middle at the arithmetic of what I'll call compact SO5, SO3 periods for a Jacquet-Langlands transfer of pi. And I'll say what I mean by all this. So the Jacquet-Langlands transfer is some kind of function that you have kind of related to pi. You'll have a function. Well, okay, so this will be an automorphic function. You can view it as a function on SO5. Some automorphic function on SO5 valued in, say, O. So this SO5 is going to be really kind of SOVL. So this is now a positive definite quadratic space that's ramified only at the prime L. And so there exists, so pi has some kind of realization on this compact on this compact group, which preserves the Hecke eigenvalues of pi, and the periods I'm talking about are what you get by integrating this function against linearly embedded SO3s. So you can see these are kind of more algebraic things because this group is compact. So in fact, this will really amount to a finite double coset space. So you're kind of talking about functions on a finite set integrated against some subset. It's a more algebraic thing. And then so you have to link these on the two sides. So on this side, the link here is through theta lifting. And what's called the Rallis inner product formula. So you have this automorphic form on SO5, that's the Jacquet-Langlands transfer. We're talking about the theta lift of that form to a half integral weight modular form on SP4 by theta correspondence. And so essentially here this L value, this is the Peterson norm of a theta lift. But on the other hand, you can calculate that these these periods are giving you the Fourier coefficients of the theta lift. So in particular, if the Peterson norm is non-zero, then you know that some Fourier coefficient had to be non-zero. So that's how the link is going between these two. And it's actually one funny thing about it is that you don't really know which Fourier coefficient is going to be non-zero. So in fact, this means that you can't really control B. So kind of the different B's will correspond to different Fourier coefficients in the end. And you kind of don't know which one you'll land on. Okay, and the second link here is much more geometric. So this is a purely geometric calculation involving the special fiber of this Shimura variety for VQL. So this Shimura variety is bad reduction. A priori, it has some kind of quadratic singularities, but you can blow them up and get a semi-stable model. So you have some kind of semi-stable thing, and you're looking at the ramification of the Abel-Jacobi image. There's a way to compute that purely geometrically using the weight spectral sequence, which was worked out in detail by Yifeng Liu. And so ultimately what's going to happen is that the ramification can be computed in terms of the geometry of how your special cycle is intersecting the different strata of this semi-stable model. And when you do this calculation, it turns out that it's sort of exactly determined by periods of this shape. I have a few extra minutes, so maybe I'll just very quickly sort of write down the key diagram for step 2 to hopefully make that a bit clearer. So the picture looks like this. So this is what I'm about to draw is essentially the sort of output of studying the weight spectral sequence for this variety. So you start, I'll put it over here. You've got the Galois cohomology, the local sort of inertia Galois cohomology of your Shimura variety. And I'll leave off a few of the decorations. And there's a particular piece of it that's picked out by the weight spectral sequence. That's the -1 part of the filtration. And there's a map from here to, in fact, your coefficients O, sort of O-valued functions on a corresponding Shimura set, which is a finite double coset space for this positive definite space VL. And this is modulo some level-raising Heck operator at Q. And so what's happening here is if you take an Abel-Jacobi image of any kind of cycle, the way you'll compute its image under this map is by intersecting, sorry, I should have mentioned, the relation of this to the special fiber is this index is the supersingular locus. So the supersingular locus of the special fiber here is 2-dimensional. And the indexing set for it involves this Shimura set. So to get the to evaluate this map on an Abel-Jacobi image, what you have to do is intersect the physical cycle, which is 1-dimensional, with the components of the supersingular locus, which are all 2-dimensional. So you get numbers, and that gives you a function on the Shimura set. And yeah, so you have this, and then of course this sits inside the full local ramified Galois cohomology. So you can see that sort of roughly the way this is going to work is you'll, you're kind of, to show that something is ramified, you're going to be sort of combinatorially looking at how it's intersecting different parts of the supersingular locus, and then applying some kind of function on this, which will correspond to the Jacquet-Lagrange transfer. And because this is sort of all very group theoretic, when you calculate on the special fiber, it's kind of the same sorts of group embeddings that correspond to the special cycle on the generic fiber. So that's why you get, again, these SO3s inside SO5. And I guess I'll stop there. Okay, thank you.
Questions?
I'm very curious. You run one case, did you prove by Euler system or by different method?
So very similar method. Yeah, what you would just sort of first you have to make sort of a level raised thing here, and then you'll use that to produce another ramified class. So it's this kind of bipartite.
Switch Shimura.
Yeah, exactly. Yeah.
So you don't really construct the Kolyvagin Euler system.
Yeah, it's not a real Euler system. It's a bipartite kind of construction. Yeah.
Excuse me. Did you expect the level raising, or did you not?
It's expected, yeah.
No, do you explain it here?
Oh, do I explain it? No, I can explain it using this diagram, actually. Okay. So I've explained...
And
yes.
Before, so this will just apply to those cubes. This is a conditional cube. Right?
That's right, yes.
And before you explain the level raising, here there is no relation, like in the Kolyvagin theory. You don't need anything like this. Is that correct?
Yeah, that's correct. Yeah. So yeah, but I can explain how the level raising works. So in fact, you really get it from this same diagram. So let me explain that. So this actually lands in the Frobenius equals 1 eigenspace. And the relevance of that is that if you had a level raising map, then you would get from here to the cohomology like this with the Frobenius is one part. And this is actually free of rank 1 under the level raising condition. So in fact, the way you actually get this is by really lifting. What you actually do is, okay, you have your Jacquet-Langlands transfer already, which goes from here to like O mod p to the n or whatever you. So you have your Jacquet-Langlands form. You're evaluating it here. This Hecke operator is measuring the depth of the level raising congruence at the prime q. So that will sort of control what power of p you get here. And so in fact, okay, so let me back up. Just from having this diagram, you can already see that the Hecke eigensystem of pi is appearing here, because this is, I mean, yeah, these are surjective, so it's going to appear here. And so in fact, to actually get the level raising map, it turns out that it suffices to get a map like this. From there, you can, yeah, this uses some kind of typicness result about the shape of this cohomology, that sort of, once you understand the Hecke module structure, you understand the full Galois structure as well. So you want to lift this map as Hecke modules, and you have it on this piece. So then there's some argument that involves sort of controlling some congruences to make sure that this will actually be liftable. But once you have that, then you construct. Essentially, you construct everything so that this diagram is commutative, so that you're actually computing the correct ramification.
And these congruences are read on the Galois representation.
Sorry?
They are read. They look up.
That's right. Yeah. So on the Galois side, they look like having Q1 alpha Q over alpha, for alpha sort of not in some forbidden list. Yeah.
And it's crucial that you have O over Qn and not O over Q. That's what you said at some point, or not?
Oh, over Pn.
Over Pn, yeah.
Yeah. Well, you could still get the statement for all but finitely many p, but if this is going to be helpful, you'll need those SO5, SO3 periods to actually be non-zero, kind of mod p to the n. So in order to be flexible about that and sort of have it only depend on the L value, it's nice to allow this to be mod p to the n.
And I'm sorry, just the last question. Here you have local trivial local systems.
Yes.
Is it correct? And is there any idea how those cycles could be constructed when you have a local system?
I don't know. Yeah.
Okay. Yeah, other questions? Okay, let's thank Naomi again.